Jingyin Huang from Ohio State University, who's going to tell us about the K-pi-1 conjecture for three-dimensional Artin groups.
Thank you for the introduction, and I thank the organizer for the invitation. It's my great pleasure to be here. So maybe I start by reminding you some definitions. Okay, so I start with Coxer group. Recall that a Coxer group is a group with the following representation. I have a bunch of generating set, finite generating set, and there are two kinds of relators. First, I demand that each relator has order 2, and second, for each pair of relators, Vi and Vj, which are Vi is not equal to Vj, we have this other kind of relator, which is Vi Vj to the power Mij equal to 1. Here, Mij is some integer which is bigger than 2, and we allow, in our convention, we allow Mij equal to infinity. It just means that there's no relation between Vi and Vj. Okay. So the Coxer group comes from a geometrical origin. So and then this relations carry some geometric meaning. We should really think Coxer group is some group acting on some space such that each generator acts as a reflection. So and then this Vi Vj to the Mij equal to 1 tells you what's the dihedral angle of the reflection. So this is the usual picture we see in the Euclidean plane. If Vi is a reflection along this line and the Vj is a reflection along the other line, then Vi Vj to the Mij equal to 1 just means the dihedral angle between them is pi over Mij. Okay. So that's the definition of Coxer group. And then I want to introduce a convenient notation for denoting a Coxer group called Coxer diagram. So the Coxer diagram is just I want to encode the presentation. So the vertices are corresponding to the generators. And then we say two vertices are joined by edge enabled by Mij if I have this relation with Mij b equal to 3. So another way to say what is a Coxer diagram is that basically the vertices are the generators, and I join two vertices by edge if this generator does not commute. Okay, because when Mij equal to 2, these two reflection meet at right angle, they commute. So that means a short description of the Coxer diagram is just a diagram describing the non-commutativity of the generators. And then I also label this exponent so I know what's the degree of non-commutativity. Okay, so that's my convention. So this is slightly different. So I must say that there's another convention to use a graph to represent a Coxer group, so-called presentation graph or defining graph, which is different from the Coxer diagram. Okay, so so now our second main player in this talk will be Artin group. Turns out for each Coxer group, I can associate Artin group. It's going to have the same set of generators, but it only have one relators. Basically, I have this kind of break type relator, so of this alternating word Vi, Vj, Vi of length Mij equal to this other alternating word starting with Vj. So basically, this Mij is exactly the same Mij as before. Okay? So that's the definition of Artin group. So examples of Artin group, including right-angle Artin that correspond to the case of the Mij is equal to 2, that means they commute, or equal to infinity, it means there's no relation. And another well-known example is the braid group. They all have presentations like this. So right now we understood lots of things about Coxer group, but we understand very little about Artin group. And then we have this very important conjecture, which is about a deep relation between Artin group and Coxer group. It says the following. So for each Artin group, I'm going to, there's some space called orbit configuration space you can construct from the associated Coxer group. So which is going to be some nice complex manifold. I'm going to say something about what is this space later. And the conjecture says that this nice complex manifold you can construct from the Coxer group is a Ka1 space. That means the fundamental group of this manifold is going to be equal to your Artin group. And then all the higher homotopy group vanishes. So this conjecture actually play a fundamental role in the study of Artin group. For example, the group cohomology, or more fancy versions of cohomology like L2 cohomology of Artin group are computed modular this conjecture. And also, if you're staring at the if you're staring at the presentation, you may expect the Artin group is torsion-free, but unfortunately, we don't know that. But if you know the K-pi-1 conjecture, it implies the Artin group is torsion-free. And also, there's a recent work by Jankiewicz and Kevin Shreve says that if you know this conjecture, then you know how to compute the center of this group. And there's also a recent archive preprint says that if you know this conjecture, then you can deduce something about the first order theory of Artin group. Okay, so this conjecture appear in various aspects in the study of Artin group. And also, I want to say, so you see probably these names, they're not really people working in geometric group theory. So this corresponding to the historical origin of this conjecture is come from singularity theory. So in the 1950s and the 60s, so people were studying certain topological space arising from the deformation of singularity, and it turns out that for some of this space, it is exactly the orbit configuration space of some Artin group. Okay, but let me don't pretend that I'm an expert on singularity theory. I believe if Misha is here, he will be able to say much more about the singularity theory side. Okay, so this is the conjecture. And then, so now I want to give you some idea about what is this orbit configuration space is. So I don't want to define for all Artin group. I want to just define for a particular case, so for braid group. So, okay, so recall that for Artin group and the Coxeter group come in pairs. So what is the Coxeter group associated with the braid group? The Coxeter group associated with the braid group is the symmetry group. Okay, so now I want to explain how you from the symmetry group, how you construct that space, whose fundamental group is the braid group. Okay, so I'm going to start with this this presentation representation of the symmetry group acting on Cn, just promoting the coordinates, and then so notice that this action, the symmetry group has lots of transpositions. These transpositions act as reflections, so which give you this collection of reflection hyperplanes cut out by these equations inside Cn. So now what I'm going to do is I'm going to remove these hyperplanes from Cn. So it turns out that after you remove this hyperplane from the Cn, then the action of Sn on the complement would become free. So what happens is that all the fixed points of the element is actually nice inside these hyperplanes. Okay, and then now I take this free action, I quotient out, I get a nice complex manifold without singularity. And then, so it's a classical theorem, so due to Hurwitz, that this space, this manifold we define, which is actually the configuration space of n points in the disk, for its fundamental group is actually exactly the braid group. And then we also know that the K1 conjecture holds in this special case. So in this case, it's indeed a classifying space for the braid group. Okay, so that's what this complex manifold looks like. It's very beautifully defined in the case of braid group. And then you can do something similar. Okay, so I don't want to go to the detailed definition, but let me just mention the rough idea is that in general you have to replace this Coxeter group by some more complicated Coxeter group, and you have to start with some representation of the Coxeter group acting on Cn, which is actually the T's representation. You complexify the T's representation, and then you also remove this reflection hyperplanes, but you will have infinite many reflection hyperplane to remove if you have an infinite Coxeter group, and then you will have a more complicated complex manifold. Okay, so this is what happened in general. Okay, so now, so since this is a conference on sort of related geometric group theory, so I want to give a reformulation of this K1 conjecture, which with a stronger flavor of geometric group theory. Okay, so in order to define a reformulation, I need to introduce this new this class of complex called Coxeter complex. Okay, before I actually give you the formal definition of Coxeter complex, I wanted to demonstrate a simple example. So let's start with an equilateral triangle in the Euclidean plane. Okay, and then if I have this equilateral triangle, what I can do is I can try to consider orthogonal reflection along the three sides of the equilateral triangle. So now I have three reflections. I'm going to denote it A, B, and C. Okay, and then so now it's not hard to check that these three reflections will generate a Coxeter group sitting in the isometric group of the Euclidean plane. And this triangle is the fundamental domain for the action of the Coxeter group. So the Coxeter group, the action of the Coxeter group is going to translate this fundamental domain around. You just keep reflect along the side, and then you would get equilateral tessellation of the Euclidean plane. And this tessellation is going to be invariant and your Coxeter group action, and this tessellation gives you a symmetrical complex, which is called the Coxeter complex of this Coxeter group. Okay, so now this is how the Coxeter complex is defined for this particular Coxeter group. It's a very natural object, so now we can define for any Coxeter group. So in general, how do we define the Coxeter complex? So basically, we're going to start with a generator set S, and then for each generators, little s, I'm going to consider this S hat subgroup, which is basically the subgroup generated by all the generators except this little generator, this generator little s. Okay. So now the Coxeter complex is going to be a symmetrical complex. The vertex set are all the left cosets of this sort of one generator smaller subgroup. Okay. And then a collection vertices span a simplex if the associated cosets have non-empty intersection, non-empty common intersection. Okay, so now I want to explain why this definition and this definition is the same. Okay, so let's look at this this picture. So for example, I want to describe what are the vertices in this complex. How would I do? So for example, I take this vertex. What is the stabilizer of this vertex? The stabilizer of this vertex is going to be generated by A and C and left out in B, right? And the stabilizer of this other vertex is generated by C and B and left out A. So basically, the stabilizer of each vertex is basically generated by all the generators except one generator. So now you translate these vertices around. So that means the vertices are exactly corresponding to left cosets of the subgroup generated by all the generators except one generator. Okay, so this is why we have this correspondence between this picture and that description. So it's not hard to say, see that the high-dimensional picture or cells also can be described in a similar way. Okay, so that's the definition of Coxeter complex. And so we can also label the vertices of the Coxeter complex. We say a vertex of the Coxeter complex is type S hat if they're corresponding to this left coset with S hat sub. And then there's a classical theorem tells us what the Coxeter complex looks like. So when the Coxeter group is finite, then the Coxeter complex is just a sphere. So in this case, so it turns out all the Coxeter, this corresponds to the classification of finite Coxeter group. How do you get a finite Coxeter group? Basically, what we do is you take a round sphere, and you take a tetrahedron, you take a simplex, convex simplex of certain shape in your round sphere. And then you do exactly the same thing, you reflect on along the side. And then that's how all the finite Coxeter groups come from, and then the reflection will also give a tessellation of the sphere, which is exactly the Coxeter complex of that finite Coxeter group. So that's the picture of what if the Coxeter group is finite. So if the Coxeter group is not finite, then we know that the Coxeter complex is always contractible. So now I'm going to define a completely analogous complex. Actually, this was first defined by Charlie and Davis. Okay, so I'm going to just shift from Coxeter group to Artin group and do exactly the same thing. I define the Artin complex of Artin group to be a symmetrical complex whose vertices are all these left cosets with this S hat subgroup. And then collection vertices span a simplex if the associated cosets have no empty common intersection. And then, so now I want to say something about the Artin complex. We say our Artin complex is spherical if the associated Coxeter group is finite. So now, so analog to what happened in the finite Coxeter group case, so what we have this theorem by Denin, it says that if your Coxeter group is finite, that corresponds to a spherical Artin group, the associated Artin complex is not exactly a sphere, but it's a wedge of spheres of the top dimensional. So homotopy to a wedge of spheres of the top dimension. Okay. And then, so now maybe I should give you some idea of what the Coxeter complex, what the Artin complex looks like. So this is a picture of the Coxeter complex. So let's try to draw some very rough picture of what the Artin complex looks like. So if your Artin complex, again, your fundamental domain would be a single simplex. And then, but now your generators have infinite order. So that means on each side, you will have infinite many triangles branch out. Okay, so that's sort of a rough picture of what the Artin complex looks like. And then, so it's more sophisticated. But there's one thing is that the Artin complex looks a little bit like a building, just for this example. So what we know is that in the Artin complex, I still have this lots of flats like this. And the Artin complex covered by flats. But this is not exactly a building because we don't know, it is not true that every two vertices are contained in the same flat. Okay? So that's sort of picture, rough picture of Artin complex you should have in mind. And that also sort of gives you a rough idea why here I have a variety of infinite many spheres rather than one sphere, because there's lots of branching going on in the Artin complex. Okay? So now by analogy, you would expect that if the Coxeter group is infinite, then the Artin complex would be contractible. And there's a theorem by Godel and Paris that this is exactly corresponding to Artin groups, all Artin groups satisfy K-1 conjecture. So this is a reformulation of the K-1 conjecture Artin group. So basically, all you need to do is to show that whenever you have any infinite Coxeter group, the Artin complex is contractible. Okay. Okay, so now I want to define another quantity of the Artin group called dimension of the Artin group. So, so let's take an Artin group. We define the dimension of the Artin group is going to be maximum cardinality of this subset of the generator, such that this sub-Artin group is spherical. So basically, I just measure what is the largest spherical Artin subgroup of my Artin group. So that is defined to be the dimension of the Artin group. So why we define the dimension to be like this? Because of the following conjecture, which is called dimension conjecture sometimes. So it says that the following quantity are the same. So the first quantity is this dimension we just defined as it is, and the second is the cohomology dimension of the Artin group. And the third is the minimum possible dimension of finite K-1 for this Artin group. And the last is the maximum rank of Zn subgroup of the Artin group. It's conjecture that they're all the same. And then again, so if we know the K-1 conjecture, then we will know the dimension conjecture. So that's why you sort of this would be a reasonable definition of dimension for Artin group. Okay. So now I'm ready to state the main result. With Piotr Prisky, we proved the K-1 conjecture holds for Artin group or Artin group with dimension at 3. And so also for higher dimensional Artin groups, we also have results. Basically, for each dimension, we produce infinite family of Artin groups whose K-1 conjecture was not known before. But unfortunately, our result in high dimension is much less complete. So in today's talk, I'm going to just focus on the dimension 3 case, which is already interesting enough. If I have some time towards the end, I'm going to say a few words about what we did in high dimension. Okay. So as a corollary, we can get some new results on Artin groups. So first, we know that the Artin group is torsion-free and have trivial center, and that's spherical and satisfy the dimension conjecture. Let me also mention a few closely related results. So the K-1 conjecture for two-dimensional Artin groups was a major result by Charlie and Davis 30 years ago. And then there are a few works between. So there's some partial result of three-dimensional Artin group by Charlie in the beginning of 2000. And also my former PhD student, Catherine Goldman, also write a paper with his co-author on the K-1 conjecture earlier this year. Okay. So now I want to say something about, now in the rest of this talk, I actually wanted to say something about, explain some of the ideas which goes into the proof of the theorem. So let me mention that we're going to prove the theorem in 2 steps. The first step is that actually most of our effort is just to prove the K-1 conjecture a single Artin group. So basically the major step is to show the Artin complex of the 353 Artin group is contractible. A 353 Artin group just means the Artin group has the Coxeter diagram like this. So let me remind you that if two vertices are not joined by an edge, it means they commute. Okay. So now somehow once we know how to deal with this special Artin group, then we can actually deduce the K-1 conjecture for all Artin group without too much difficulty. Okay, so now there are 2 things I need to explain. The first thing I want to explain is why is this single Artin group so special in the whole picture. Okay, and the second thing is that how do we actually deal with this single Artin group? Okay, so maybe I'm first going to explain why this 353 Artin group is so special in the whole in a class of all 3-dimensional Artin group. Okay, so this is related to the way of how we prove the K-1 conjecture. So we want to do some kind of induction. So I'm going to take an Artin group generating set S, and recall that the vertices of the Artin group has type S, has type corresponding to which coset they correspond to. Okay, so now we want to prove the Artin complex is contractible, so that's the geometric group theory reformulation of the K-1 conjecture, by induction on the number of generating set. Okay, so now what we want to do is the following. So I'm going to take a vertex of type S hat, little s hat. And it turns out the link of this vertex is going to be an Artin complex of a smaller Artin group, which is generated by all the generators except little s. Okay? So now you see that this gives us some chance to do induction. So if this smaller Artin group is not spherical, then by induction, the link is this small Artin complex still contractible. Okay? So now what you know is that if you are in a complex, let's say this is your complex, if you have a vertex such that you know if you know the link of this vertex is contractible, then what you can do is you can remove the open star of this vertex without changing the homotopy type of the complex. So this means that basically the Artin complex homotopy equivalent to the subcomplex with open stars of all the vertices of type S removed. Okay? So in this case, we can play this trick. And hopefully you can, the plan is to keep doing deformation retract to small and small subcomplex. But there's another case. So if this small Artin is spherical, then we know the link is homotopy to a wedge of spheres by Dinin, and there's no way we can play this trick. Okay? So that means there's this base case of the induction, which is corresponding to we cannot perform this kind of trick. So this base case is exactly corresponding to Artin group, which are almost spherical. That means those Artin which is not spherical, but as long as you remove one generator, it becomes spherical. Okay. So now I'm going to focus on how we deal with the almost spherical Artin group. So basically, there's actually a previous approach by Chad and Davis. So basically, I need to show, I'm going to assume my Artin is almost spherical. And then Chad and Davis proposed an approach that if you are able to motorize the Artin complex as a Cat0 space, then you will know this is contractible and you're done. Okay, they actually managed to do it in dimension 2, which is actually a highly non-trivial result. Okay, so now, and then I want to explain to you how do we motorize this. Okay, so there's a turns out to be a natural metric on the Artin complex. Okay, so what's a natural metric? So to motorize the Artin complex, we know that the fundamental domain of the Artin complex is a single simplex. All I need to do is just motorize the single simplex, and then I use the group to translate it around. Okay, so now in order to motorize the fundamental domain, I'm going to use this theorem by Nanner in the 1950s. So it says that if your Coxer group, okay, so they come in pair, if the Coxer group is almost spherical, then the Coxer group, there's not too many of them, they actually properly co-compact by isometry on Euclidean space or on hyperbolic space up to dimension 4, with fundamental domain being a compact simplex. Okay, so now you see that you have a natural metric of what is your fundamental domain. You just motorize the fundamental domain of your Artin group with this whatever shape you get over here. Okay, so that's a natural metric on the Artin complex. And the conjecture would be that if we motorize the Artin group this way, then the Artin complex would be Cat0. Okay. So now I want to explain that so this is somehow what inspired us in the first place. So however, there's some obstacles to prove this complex Cat0 in dimension beyond 2. I want to explain what are the obstacles to prove this complex is Cat0. Okay, so first, how do we prove something is Cat0? There's one common criterion everybody's using. We need to check the link of each vertex, which is a piecewise spherical complex, that is Cat1. And then how do you check something is Cat1? So there's a criterion by Bowditch, or there's several criterion. Let me just mention one of them. So it says that compactio, that's a metric space Cat1 if it's locally Cat1, and any loop of length less than 2 pi is 2 pi homotopy to the trivial loop. 2 pi homotopy means that you homotopy through loops of length less than 2 pi. Okay. So now, basically, okay, so there's a small thing that our complex, the Artin complex, locally infinite. So the link are actually not compact. So there's a small problem here, but it turns out that you can generalize Bowditch's theorem a little bit to cover some non-compact case. So that's not a big problem. So, okay. So now what we need to do is to we need to study loop of length less than 2 pi in this spherical complex. Okay. So Gromov famously did this for Cat0 cube complex, right? So this is actually quite doable for Cat0 cube complex. But we can analyze loop of length less than 2 pi, and there's a nice flag condition we're going to propose. But if you complex the shapes a bit funny, then there's no such good thing. So now the next observation we need is the following observation by Ruth Charlie. So what she says is that if I give you a loop, if I want to study a loop of length less than 2 pi, I try to relate it to a group theoretical information. Okay. So what she observed is that each loop will give you an equation or system equation over the group of this form: x1 times x2 times all the way to xn equal to 1. 1 means the identity element in the group, subject to the constraint that each variable lies inside a prescribed parabolic subgroup of the Artin group. Okay, a parabolic subgroup is just a subgroup generated by field generators. Okay, so so this is the kind of thing. I can say a bit rough. What's the rough idea of you get this equation? Basically, you look at this loop. This loop is going to pass a bunch of simplices. Each simplices would have some stabilizer, and then this prescribed parabolic subgroup is going to be just the stabilizer of that simplices. And then, so that means that each variable corresponds to which simplices you pass through. Okay, so that was Charlie's observation. Okay, so now, you see that we translated this problem into a group theoretical problem. If I can solve this equation, I can probably say something about this loop. But there's another thing you need to worry about is that, okay, so this is just one loop, but I have to deal with all loops of length less than 2 pi. Okay, so but there's another observation by John McMahon says that actually we only need to solve finite minus such equations. Okay, so finite but possibly huge number of such equations. Okay, so now this is the task we need to do in this case to prove Cat1, hence Cat0, is we need to solve these equations, and then if you manage to I just say something about the solutions of this equation. If you manage to do that, then you prove Cat0. Okay, so now this is where the difficulty comes from, because first we know that there's a famous theory of solving first order equation on the hyperbolic group, but notice that these equations are not belong to the first order theory of your group because of this constraint. And second, your group is not hyperbolic or radical hyperbolic or cylindrical hyperbolic. And the third, even if you had a robust theory of doing this, so this equation can get pretty long and the number is huge. Even in dimension 3, the number of equations you need to deal with is huge, and this equation are usually pretty long. And another thing is that the number of equations you need to solve will blow up as the dimension go to infinity. Okay, so that's some of the obstacles you need to overcome to follow this route. Okay, so now after some struggle, so we decide to trying to find ways to get around this obstacle. Okay, so basically what I want to do is the following. So let's say suppose I'm going to give you some simply connected simplicial complex of certain kind, and I want to find a simpler local condition which guarantee the contractibility of the complex. Okay, so notice that here what I want to do is I don't claim I know how to prove the complex Cat0. I just want to say that I hope to find a local condition where proof the space is contractible. That would be good enough, at least for proof K1 conjecture. Okay, and the contractibilities are actually a much weaker condition compared to proving something is Cat0. So this gives me some room to play. And also, I hope that I'm able to find this link condition, local condition, is a bit simpler. So I'd be pretty happy if you tell me that I only need to solve 2 equations. Each equation have 6 variables. I'd be happy. But if you give me an equation with 100 variables, I'll be less happy. So that's the kind of local condition I'm trying to looking for. And one more thing is that notice that here I'm saying local condition. I didn't say link condition. Because I think link condition is the best kind of local condition. You just need to look at that small vortex, a small ball around that vortex, right? But I'm slightly relaxing, so I'm saying local condition, I'm giving myself a little bit of room. So if I have a condition which is about like 2 ball or 3 ball, that would be not so bad. Okay, so that's sort of the kind of thinking behind this. Okay, so that's what I want to do. But before I tell you, before I explain how to do this for, let's say, for 353 Artin group, there's another thing I need to explain. So there's another sort of obstacle, which is that, okay, no matter whether you decide to follow the Kaiser approach or you want to do this workaround, then it's not hard, then you would expect that the list of conditions you need to check depend on the shape of your simplices, right? For different shape of the simplices, no matter if you do the Kaiser one or do this one, you would, it's natural that you might have a different set of conditions to check. So that means if you have too many shapes of simplicity to work with, then you might have too many set of conditions to check. That could be potentially be a problem. Okay. So now the next thing I want to point out is a way of reduce the number of shapes you need to deal with substantially. Okay. So I start with the following definition. So I'm going to say that one Artin group dominates another Artin group if there's a bijection between the generation set such that for any pair in S, the exponent between S1 and S2 is bigger or equal than the exponent between their images. Okay? So the vague intuition is that if AS dominate AT, then AS is more hyperbolic than AT. Okay? So for example, the free group, where all the exponents are infinite, would dominate everything else. Okay? So this is some kind of comparison geometry, if you like. So now we're going to say an almost spherical Artin is tight if it does not properly dominate another almost spherical Artin. Proper means that one of these inequalities is actually strictly equality. Okay, so now the nice thing is that the tight almost Artin group is much shorter than this. So this is a lemma that if almost spherical Artin group is tight, then it's either Euclidean, so that means the corresponding Koster group acting on the Euclidean space, or this 353 or 5333. Okay, so now you see that why 353 is sort of the quite special for us because in dimension 3, so this 533 is a 4-dimensional one. So if you just care about dimension 3, then the 353 is the only non-Euclidean shape we need to care about. Okay, so now using this notion, we can remetrize the Artin complex. So what I want to do is I wanted to take an almost spherical Artin group. And I'm going to find some other tight almost spherical Artin group dominated by this Artin group. Okay? So what I want to do is metrize the fundamental domain of my original Artin complex with the fundamental domain of this tight Coxer group action. Okay? So the example you could I think it's better I give you an example of what is exactly I'm doing over here. So let's say suppose I give you a Coxer group, looks like this, 3, 3, 4. Okay, this is a Coxer group. Okay, and then so we know that if you we know this is actually a hyperbolic Coxer group. If you want to metrize, you better metrize the fundamental domain as a hyperbolic simplex, right? But what I want to do is I want to find a tight Coxer group dominated by this Coxer group. So what would be that? That would be a 3, 3, 3, 1. So that's a Euclidean one. And then what I want to do is basically I'm going to metrize each simplex here by the equilateral triangle. And you see that it would work because of the Ning condition. Okay, not have to check. Okay. So that is what we are doing here just to reduce the number of shapes we need to use using this kind of comparison geometry thinking. Okay. Okay. So now finally I'm ready to explain. So what is this local condition I want? So how we find this local condition on the 353 Artin complex, which would imply the contractibility of the Artin complex. Okay, so here's the plan. So first, the Artin complex is sort of mysterious and hard to understand. So I want to start with something easier. So I want to start by solving the same problem for the 353 Coxer complex. We understand the Coxer complex much better. And okay, so this sounds a bit funny because okay, so we already know the Coxer complex is contractible because it's just tessellation H3. So what is exactly the thing we need to do? So the thing we need to do is we want to forget about the contractibility of the Coxer complex. What I want to do is I want to look at what is this combinatorics of this Coxer complex. I want to find local combinatorial pattern which leads to contractibility, and I want to axiomatize this local combinatorial pattern and then apply this to the Artin complex. That's my plan. Okay, so I'm going to stare at the 353 Coxer complex for knowing enough. I hope I can find some local combinatorial condition which leads to the contractibility and axiomatize these conditions and apply this to the Artin complex. Okay, so now for that purpose, we have to stare at this picture. So Okay, so what is this picture? So this picture, I take it from Wikipedia because it's too hard for me to draw. So, so this picture is a picture of a tessellation of the hyperbolic 3 space by regular isocahedrons. So it's amazing that you can tie H3 by regular isocahedron, and this is a picture of it. And then, so what's the relation between this icosahedron honeycomb and the 353 coxal group? So what we know is that the symmetry group of this honeycomb is exactly the 353 coxal group. And the barycentric subdivision of the cell complex you see is exactly the 353 coxal complex. Okay, so that's the relation. So that means, well, because I said earlier that I just want some local condition. I give myself a little bit of flexibility to look at spaces which are not exactly the 353 complex, but somehow closely related. Okay, so now let's look at this honeycomb. And what we want to understand is, okay, this honeycomb is made of these icosahedrons. And what I want to understand is how these icosahedrons intersect each other in this honeycomb. And I hope to extract an intersection pattern of this honeycomb, which would lead to contractibility of the space. So that is my goal, okay? So now, in order to understand the intersection pattern of all these 3 cells, I want to introduce an auxiliary square complex, okay? So I'm going to take Z to be this 3-dimensional honeycomb, okay? Each cell isocahedron. And then I want to define an auxiliary square complex, which help us to understand the intersection pattern of these cells. So this complex was actually started by Nima Holder in his PhD thesis. So we just take his idea. So basically, the vertices of this complex are either the original vertices of your 3-dimensional complex, which we call the original vertex, black vertex, or the center of the 3-dimensional cell. We call them white vertices. Okay, so that's 2 types of vertices, black vertex and white vertex. And then, well, we define the edges. So we say a black vertex is connected to a white vertex if the black vertex is contained in the 3 cell with this white vertex as a center. Okay. So now this is my edges. So the edge is just corresponding to which vertex is contained in which 3 cell. So that's exactly what we want to understand. And I want to emphasize that this Z had some edges by itself, right? I'm going to ignore all the original edges of Z. And these are the only edges I'm considering, okay? So this will make the one skeleton become a bipartite graph, right? Because I have the black vertices and I have the white vertices. All the edges are between black and white, okay? And then, so now I'm going to attach a square for each 4 cycle in the one skeleton to obtain a square complex. Okay, so that's a square complex I'm considering. And then, okay, so it turns out that this square complex is simply connected. So now the first observation we had is that this square complex is sort of non-positive curve in the following sense. So okay, so we still want to looking for non-positive curvature because it's a classical relation between non-positive curvature and contractibility. But we might want to looking for maybe weaker notion of non-positive curvature. Okay, so what's the form of non-positive curvature you get? Okay, so now what I want to do is I want to understand minimal combinatorial minimal disk in X. So basically what we did is we take a loop. I'm going to take a loop in the one skeleton. And I want to fit in this loop by squares. Okay? And then let's say we had a disk. And then I define the area of this disk is just how many squares you need to fit in this loop. Okay? And the minimal disk would be just you fix the boundary and you want to find the filling with the minimum number of squares. Okay? So this topologically you may not get a disk, but let's ignore that for the moment. Let's pretend that we did. If I give you a loop, you did get a nice disk tessellated by squares. Okay? Okay, so now I want to say, if you're trying to consider this kind of combinatorial minimal disk in the complex, then it has the following features. Okay, so the key point is, I'm going to draw some picture. Okay, so I want to, okay, so another thing is I want to motorize each square as just the flat square of right-angled in the Euclidean plane. So that's the metric I put in the square. So now I want to ask myself, is this minimal disk non-positive curve or not? Okay, so unfortunately, this minimal disk with this metric is not non-positive curve on the nose because you would have things like this. Okay, so you have vertex of minus 3. So this is a standard example of a positive curved vertex, right? But the good news is that whenever you have a positive curved vertex, namely like degree 3 vertex, then all the adjacent vertices has to be degree 5. So this comes from the, if you are in a minimal disk, then this is what happened. Okay, so that means whenever you see some positive curvature, it's immediately balanced out by some negative curvature vertices. And also this third condition basically says that if I give you a negative curvature vertex, you don't have too many positive curvature vertices dragging down. Okay, so somehow it's a simple computation by just using these numbers. You realize that this disk is not non-positive curved on the nose, but if you become a bit larger, it's sort of non-positive curved in average. It's actually negative curved in average. Okay, but this is not so surprising because we start with the tessellation of H3. So this is actually what we expect to get, right? Okay, okay. So now we're not there yet. Okay, so now notice that this tells you. Okay, so now we begin to see some trace of non-positive curvature or combinatorial form of non-positive curvature or negative curvature, and then but this remember our task is to find something which is local, but this is not a local feature because this is a statement about combinatorial minima disk. So it's a statement about the minima disk. That's not a local statement because to say this disk minimum, you have to compare to all other disks, right? That is not a local statement. Okay. So now our next step is to boil this down to a more local statement. Okay. So now this is actually a few things we observe from this honeycomb. So it says the following. So let's look at the first thing. So we observe that okay, we look at the local disks in your complex. The first rule is that whenever you see a disk made of two squares looks like that, then you can keep the same boundary and fill in another disk on the back. Okay. So this is a sort of a replacement rule. That means whenever you see this configuration, you can replace that configuration. So once you have this local replacement rule, it immediately implies that in a minimal disk, you can never have configuration like this. Because when you have configuration like this, you do the replacement, then justify your disk is not minimal. Okay? And then similarly, I have a few other configurations. So here is a configuration, bad configuration. It's like a vertex of Venus 3 is adjacent to another vertex of Venus 3, which is not something I like. I want all the labels have Venus at least 5, right? So now what we observe is that once you have this local disk in your complex, then one cube corner is not minimal. A cube corner is basically this configuration made of 3 squares. Okay, they form a corner of a cube. So this is what might be mean by cube corner. And we say the cube corner is not minimal means that so the boundary cycle, which are 6 cycles of this cube corner, actually bound only bound 2 square. You can find alternative filling with 2 square. Okay. So again, so this would allow you to decrease the area of disk. So this would justify this kind of configuration never appear in a minimal disk diagram. And there's a similar one. This one is basically Venus 3 vertex adjacent to Venus 4 vertices. And then also we managed to use the combinatorial honeycomb to find a replacement to decrease the area. And this is another thing is that if I have Venus 5 vertex, which are adjacent to too many Venus 3 vertices, and then we can also find some replacement. So now, basically, this is the local feature which will ensure that your disk diagram is sort of minimal disk are sort of non-positive curved and negative curved in average. Okay. So now, and these are the features we want to axiommatize. So we say that a 353 square complex is going to be a simply connected square complex with bipartite one skeleton satisfied above disk diagram replacement rule. So that means whenever you see these 4 types of disks, then you can do replacement like this. Okay. So now notice that I didn't list all the disks you need to replace. So it turns out that okay. So this is something I'm going to say later. Okay. So that's the definition of 353 complex. Okay. So now it turns out that this 353 complex have feature of non-positive curvature. So this turns out to be a version of Cardan-Hartman theorem. We're able to say what's the distance function in the large scale. And they have corrective function both in the complex has weak form convexity, etc., etc. So, but the most important thing is we have we need contractibility. But you see that from this definition, your complex is not contractible. Just look at the first thing. So this two square in the front and this one square on the back would bound the sphere, right? So this is not contractible because your complex is two-dimensional. To fix this problem, so I'm going to define what we call the thickening of a 353 complex. We say that, okay, so I'm giving you a 353 complex. We say two vertices are closed if they contain in a common square. Okay, so now I define the thickening of this complex to be the flux simplicial complex whose one skeleton is basically the original one skeleton, but I have to add more edges between the vertices which are closed. Okay. So in general, this will give you an infinite dimensional flux simplicial complex. Okay. So now we have the theorem we proved is that the thickening of a wide stable 353 square complex is contractible. So that's two minor assumptions. So because this square complex we have the actual application in the actual application, these square complexes are not locally finite. So we add two minor conditions, which I don't want to explain right here, but they are very minor conditions and very natural conditions, and we show that the thickening is always contractible. Okay? And so this is something. So this is basically for this kind of non-positive curvature we extract, and which is a local condition, right? This is a local condition, which implies the contractibility. And then now I'm going to apply this to the Artin group. So how do I get a 353 square complex from the 353 Artin group? So basically I start with the Artin group, and then I'm going to consider a square complex whose one skeleton is the AD subgraph of the Artin complex. So basically recall that the vertices of the Artin complex are labeled by A, B, C, D. So now what I do is I just take those A vertices and D vertices and take the edges between those vertices. So this is what I call the AD subgraph. So now I take that as the one skeleton of my square complex, and I attach a square for each 4 cycle. And now I get a square complex. It turns out that this square complex, wide, stable 353 square complex, and moreover, the thickening of X is homotopy equivalent to the Artin complex. So if you put these two things together, you will finish the proof that this complex is contractible. So now I want to say a bit more, because so far as you can see that this condition we need to check, the square complex is 353 complex, is a local condition. And then we have to relate it to a 353 Artin complex. It sounds like a terrible local condition to check, right? So you might have to, because when you relate different things, you might lose control. You have to go to 3-ball or 4-ball, right? So, but surprisingly, so somehow to check X is a 353 complex, you can just reduce to checking a link condition, okay? So it looks like the 353 condition concerns disks which are much larger than the link. But surprisingly, in the end, we actually reduce to check a link condition. And I can show you what is exactly link condition we need to check, okay? And we can compare that to the link condition we need to check for cat 0. Okay? So now, for example, I'm going to take a vertex of type D hat. And then what we know, the link of this vertex is going to be a smaller Artin group, generated by ABC, and it's Artin complex. In this case, it's the Artin complex spherical Artin group type H3. It's an exceptional type Artin group. And then, so it turns out, modulo some previous work, it turns out that to check in, I get a 353 complex. The properties you need to check, there's only 2 things you need to check for the link of this vertex. Okay, the link of this vertex is this delta ABC. So there's only two types of cycles you need to check. So the first cycle is, okay, so this means that I have an A cycle, and A means because the vertex type, so this A, C, and B, they're the vertex type of the cycle, okay? So the first condition is that I have this 8 cycle that I need to check. This is not embedded or not induced. And the second condition basically says that I have this 10 cycle, then I need to check that it's an induced embedded cycle, which is already induced embedded, then can find some kind of center of this cycle. So that's sort of the condition we have to check. So now I want to explain how is this condition related to the cat 0 or cat 1 condition, okay? So the first thing is that all these cycles are length less than 2 pi. So this is a strict subset of cat 1 condition, okay? And the second thing is that so somehow if you want to check cat 1, then this will be much longer. Okay, so that's sort of what actually make us manage to do this. So to check these conditions, what you need to do is basically as before. So if so there's another comment I want to make. So let's look at the first condition. So the first condition says that I give you an 8 cycle. Let's say this is 8 cycle. Okay, I didn't draw an 8 cycle. And then it says that this 8 cycle is not embedded or not induced. Let's say this 8 cycle is not induced. What does this mean? It means that probably you can find a shortcut somewhere, right? And if you have a shortcut somewhere, it means that you cut the 8 cycle into smaller cycles. And then, so now you can try to fill in, maybe the simplest case is you just have this, right? And then you have this, that it tells you how to shrink your cycle, right? Because you can replace this 8 cycle by a 7th cycle using this shortcut. So that means this combinatorial formulation is still somehow in the spirit of Bowdish's criteria. So it tells you what is a specific combinatorial scheme to shrink your cycle, okay? So that's sort of there's something in common with the Cat1 condition. Okay, so now I need to explain. Okay, so now this comes from to the heart with a lot of headache. So it's how do we check this kind of condition? As I said earlier, so following observation by Rustrelli, from this cycle, I'm going to write down an equation. So this is the 8th cycle. I'm going to write down an equation which is made of 8 terms. And this is a 10th cycle. I need to solve an equation made of 10 terms. How do I solve this equation? Okay. So if I cannot solve this equation, then I cannot prove the theorem. Okay. So now the next part is I want to explain how to solve this equation. So or in other words, how to check the Ning condition. Okay. So I take this Ning, which is the Artin complex of type H3. Okay. So the sort of fantasy I have is that suppose this Artin complex is actually Cat0. We can use the Cat0 geometry to have control on the fitness of the cycle, right? So what's the Ning condition? The Ning condition we need to show is that if I give a cycle and I need to find a shortcut, okay, that's the Ning condition. One of the Ning conditions we need to check. Suppose you have Cat0 geometry. Then the Cat0 geometry tells you how to fit in this cycle by a disk, okay? And then the Cat0 geometry will give you very fine control of what is the local structure of this disk. And from there, it's not hard to find a shortcut, okay, if that's one. Okay, so that's sort of something nice. If you know your complex non-positive curvature, and then it tells you how to fit in disk. Once you know how to fit in disk with very good control on the local structure of disk, you'll be able to check all the conditions we need. Okay, so now, but Denis says that it's complex a web of sphere, so this clearly is nonsense. Okay, so what we want to do next is basically okay. So this is it's a wedge of sphere. It's not Cat0, but we want to do something slightly weaker. So what I want to do is, okay, this is not Cat0, but I can try to find the maximum Cat0 pieces inside this complex. So more precisely, what I want to do is I want to find a subgroup of your group G and the H, so the subgroup denoted by H. And I want to find the H environment, H co-complex subcomplex of your spherical complex delta, such that I can motorize this subcomplex with an H environment metric of non-positive curvature. Okay, so that's something weaker I wanted to do. And then you see that why this is helpful, because of course I want H and Y to be as large as possible, right? If this Y is large enough to contain the cycle I want to understand, then I'm in good situation. Okay, so that is the plan. So now I also want to mention that this is not completely insane, because probably already see that it's inspired by the geometrization of 3-manifold. So if I give you a 3-manifold, say you really like hyperbolic geometry, but your 3-manifold may not be hyperbolic, then you can force the hyperbolic geometry on the 3-manifold. Your 3-manifold will break up into pieces, and you may be able to find a larger hyperbolic piece. And here we're doing something similar. So it's not a 3-manifold, but we have a group angular complex. And okay, so I really like Cat0 geometry, so I want to force upon the Cat0 geometry on this complex. And then I may not be able to do that. Again, my complex break up into pieces. And I want to find the largest pieces, which support the kind of geometry I want. Okay, so that's sort of the idea. And then, so now, okay, let me see. I still have a bit time, so maybe let me don't do the higher dimensional ones, I want to give you some idea of how do I find this largest complex. So I'm going to take 2 or 3 minutes to explain what is this subcomplex, how do we find them, okay? So I don't want to explain the case of H3 because H3 is actually exceptional type Artin group. Everything is a bit messy, but I do want to explain what happened to the braid group. Everything is super clean, okay? So but the idea are the same. So notice that what's the problem we want to study? The problem is the following. So I have my braid group. I'm going to acting on this spherical complex. It has a lot of spheres, okay? So now what I want to do is I want to remotorize this complex such that I want to find the largest possible non-positive curvature piece I can. Okay, so that is my task. Okay, so how do I do that? Okay, so first I'm going to consider what we call the pure braid group. So the pure braid group, so from definition we know that every braid group can map to a symmetry group by just compute the homomorphism is basically come from, you look at the permutation induced by the braid. Okay, the braid is going to permute the strand. Okay, that's the homomorphism. And then the kernel is what we call the pure braid group. Okay, so now what we know is that okay, so I can restrict the action of this action. So I have the pure braid group acting on this complex. Okay, so what I know is that this complex mod out the pure braid group is exactly a round sphere. Okay. So now this is a round sphere with a symmetrical structure. So now what I want to do is I want you to take a hemisphere. I'm going to take open hemisphere. Okay, so this round sphere has a lot of walls, right? I'm going to take an open hemisphere. So basically, let me draw a picture in dimension 2. An open hemisphere is going to look like this. Okay, so this roughly, if you open it up, it looks like that. Okay, so now what I want to do is, okay, so I have this map from delta n to Sn-1. So this is my map pi induced by this action. And I also have this open hemisphere sitting inside Sn-1. Okay. So what I'm going to do is I'm just going to consider the inverse image of this open hemisphere. Okay? And I want to say this inverse image is going to be non-positive curved. And what is a subgroup? It turns out the subgroup is just the central quotient of the pure braid group. And what is the metric? So now, okay, so there's several things I need to explain. So first, what is the metric I'm going to put over here? Because this thing is just an inverse image of that thing. If I'm able to materialize that thing, then I'm happy, right? So now you see that that's again a problem cat zero geometry because in higher dimension, it may be natural to claim I get some kind of cat zero geometry, but again I have this problem checking link condition. So now what I'm going to do is basically it's quite similar to Ursula's talk. So she said that if you don't like L2 metric, you can use some polyhedron norm. So what we're doing is we're going to put the L infinity norm on this complex, and then I'm going to pull it back. And what we showed is that whenever you put the L infinity norm on this complex, when you pull it back, you actually get an inject metric space. Okay, so that's a form of non-positive curvature. It gives you conical bicompany as mentioned in Andre's talk, and then it's strong enough to help you know how to finish the disk. So this is one way of how we find these largest pieces of non-positive curvature pieces. Okay, so maybe I think it's time for me to stop. Thank you very much.
Questions? Yes.
Could you say again what the subgroup was when you're acting on H0? So,
Okay, so
acting on the pre-image, right?
So what happened is that, okay, so we know the pure braid group split at z times something. Okay, and then, so somehow, so what happened is that the inverse image of SG0 has an infinite component. You have one component for each copy of z.
Ah, okay.
And then the stabilizer would be some sections which acting on this thing. Okay. So that means we don't really lose that much group theoretical information because it's more or less a central quotient of the braid group.
Yes, I see. I think it was because you said central quotient, but it happens to be a direct product, so it's also
Yes, yes, maybe that's, yeah, sorry, so yeah, I didn't make it clear.
Yeah. Any other questions?
Can you, I mean, have you explained how you reduce everything to the 353? I mean, how do you
Yes.
use domination?
Okay, yes, thank you. So basically the first step is to somehow reduce to almost spherical, and then use that deformation retract trick. And then once you are in almost spherical, then we just look at those tightest almost spherical.
Yeah, but why is it down?
Okay, okay, that's actually a very good question, because this is the part I didn't explain, and you caught me. So, so what happened is that okay, so let's say suppose I want to use my knowledge to understand what are the about tight almost spherical, to understand what is actually happen for all almost spherical things. So what I'm going to do is, okay, if I give you something which is almost spherical but not tight almost spherical, I can use the link condition I know for the tight almost spherical ones to check what happened to the almost spherical ones. And that is what actually happened. So that means the link condition we mentioned is not only good for one example, it's good for a few more examples. Okay. So another thing, maybe another, to answer your question, so I only explained 353. I haven't explained what happened to the other Euclidean type. Right, so it turns out that there is also a link condition. So you can do something similar. Like you have to look at those tilings and try to understand the combinatorics, and you will be able to have a weaker link condition to check compared to the cat zero condition. But the Euclidean case is slightly simpler because the picture is easier to understand.
Oh, sorry.
Sorry. Yeah. So you use this like topological reduction to the almost spherical case.
Yeah.
Can you go back and then extend your non-positive curvature to like the Artin complex or Dalí complex for the other three-dimensional parts groups of the game?
Unfortunately, no, I don't know how to do that. Yeah, because yes, that's a very good question. So probably it's not so easy to do it. I don't know the answer to your question. But thank you.
So you're putting, you sort of locally said, what you're doing to the metric. Does this actually define a metric on the whole space, or you're just working with local?
Yeah, okay, so you mean over here, right?
Yeah.
Okay, so what happened is that so I have this complex mapped down to the sphere. I take an open hemisphere, and I'm going to put L infinity metric on the open hemisphere. But then I can pull back this metric. So yeah, it's only defined on a subspace of this delta A. It's basically defined exactly on the inverse image of this open hemisphere under this projection pattern.
Right.
And then the claim is that this inverse image is an injected, each component in this inverse image
So
is
you
injected
just
matrix.
use this locally to get contractible, to show that these pieces are contractible.
I see. So this one is to check the link condition.
Oh yeah.
And then I use the injected the component to fill in cycles, which
Right.
help me to check link condition.
Okay. So you're not actually defining something on the whole space at once. It's this.
Yeah, it's this piece, and I hope, because I need to deal with this cycle, I hope my cycle get trapped in one of this piece. Then I can use the geometry of the injected matrix space to fill in the cycle and solve that equations.
You hope.
Yeah.
So why should it push down into those pieces?
Okay, so that's another very good question. So it turns out that not most, actually it's not true that all the cycles I care about lies inside one of those pieces. So, but it turns out that those cycles which does not get trapped in one piece are actually easier to handle.
Oh.
So, yeah.
So the 5333, you don't know how to.
That's a very good question. So actually, my student, like Catherine Goldman and Piotr Pitsky, they told me that they're working on this, and that they relate this to a notion called seven located, which is actually appearing in Damien Osiris some earlier work. So there's also like some kind of weaker link condition which you could possibly to use this as a replacement cat zero, but that's like a very much speculative. So we don't know for sure what to do with 533. Okay, so that's not a theorem. I'm not claiming any theorem. Yeah.
But once you can do 5333, like how, which Artin groups will you know if I look for?
I see. That's a very good question. So you may wondering how. Okay, why? Oh, okay. So what are the obstructions to okay, so these are the shapes we need to understand. So for the Euclidean shapes, we know that there's an AN2W plus there's a classification, right? So the shapes we don't know how to deal with at the moment is 533. And then for the Euclidean shape, we know how to deal with for most of them, but there's a finite many exceptional Euclidean cases. We don't know how to deal with them. Okay? So that's why there's still lots of obstacles to overcome in order to have a full treatment of K-1 architecture.
Any other questions? If not, can we meet back at 1:45? Thank you very much.